Okay, welcome back. This is Calculus 1, Lecture 5, the derivative as a function. So last time we looked at finding the derivative at a single point, but what if we want to find the derivative for every point on a function? That's when the derivative itself becomes a new function. This is especially useful when we want to know how a function is changing everywhere, not just at a single point. So for example, if you're tracking motion and how a car's speed is changing over time, you can use a derivative of the position function, also known as the velocity function. So it is its own function. Okay? So recall, we've already seen that the derivative of a function at a point x is equal to a is given by the following formula, right? This is the limit definition of the derivative at a single point. F prime of a is equal to the limit as h approaches 0 of f of a plus h minus f of a over h. However, if we don't specify an x value, we can simply leave the x in there and get a general formula for the derivative at every point x. Okay, and that's going to look much the same, but instead of an a, we've got x's everywhere. Okay, and we're going to leave that as a variable and simplify around it. Okay, so let's look at an example. We've got, given f of x is equal to 5x squared minus 12x plus 7, find the function f prime of x. So we're going to start with our general form of the limit definition of the derivative. And then we're going to go ahead and we're going to substitute in f of x plus h, which is going to have an x plus h everywhere the original had an x. And then, of course, f of x, where we're just copying the original function in. Okay, we go ahead, we expand. Okay, that's one of our special products. And we can just move this h over here. And then we can go ahead and distribute. And we're going to try to get to this point where we can now look to combine like terms. So we've got a 5x squared, negative 5x squared, negative 12x, positive 12x, positive 7, negative 7. We're going to cancel all of these out. And this is good. All of our non-h terms are canceling, and that's great because that means we can go ahead and we can factor out an h from the numerator and cancel it with the one in the denominator. Okay, and that's going to allow us to actually use direct substitution. So we can now plug in 0 for h. Okay, so originally we're left with the numerator, 10x plus 5h minus 12. We go ahead, we plug in 0 for h, and we'll be left with just 10x minus 12. F prime of x is equal to 10x minus 12. This is the general form of the derivative. Okay, and if we wanted to, we could now use f prime of x, this general form we've just found, to determine the slope of the tangent line to f of x at any x value. So if we wanted f prime of 2, we just plug in 2 for x. We'll get 8. If we want f prime of 0, plug it in, we'll get negative 12. F prime of negative 19, plug it in, we'll get negative 202. Okay? That's the value of this general form. And as we're going to see later, in addition to just finding these sorts of values like we were doing in the last section, or last chapter, we're going to be able to plot f prime of x, which has its own benefits as well. Okay? Let's take a look at example B. Given g of s is equal to s cubed, find the formula for g prime of s. We start off the same way with our limit definition formula, but this time we're going to be leaving s in there instead of x. We substitute our function, which is just cubing, so we have s of h, s plus h cubed, s cubed. We can expand s plus h cubed like so. This is also a special product. A plus b cubed, and expands in this way. We go ahead, we cancel out our like terms. I just got this written here twice, but we cancel out our like terms. This simplifies to the limit as h approaches 0 of 3s squared plus 3sh plus h squared. Plug in 0 for h. You're left with just 3s squared. Okay? Pretty simple. Now let's take a look at the case where we have a square root in our function. Okay, and for this one of our techniques from before, when we're dealing with limits, is going to have to come back to help us simplify this. So first we're going to try to find the formula for k prime of y, and then we're going to use the formula to find k prime of 4, k prime of 9, and k prime of 36. We've got our formula, same as always. Now here, we're going to be plugging in y plus h everywhere we had a y. So because this was square root of y, underneath that square root is now going to go y plus h. Subtract the original function, square root of y, divided by h. Now, we can't do anything when we have two radicals like this, not directly at least, so we're going to have to multiply by something convenient or valuable that will allow us to break out these radicals. And that's going to be the conjugate. Okay, so this technique we saw a little bit earlier when we were dealing with radicals like this, we're going to use it again, and this is, again, of the form a minus b. This is of the form a plus b. And this is going to allow us to get a squared minus b squared, which will eliminate the radicals in the numerator. Just make sure that as you do it to the top, you're also doing it to the bottom. This entire quantity is just a 1. Okay? So we don't want to be changing the value of the expression. We can always just multiply by 1 though. So as long as we do whatever we're doing to the bottom as well as the top, it's perfectly fine. So we go ahead, we multiply those, and we get exactly that. We have our a squared term, so the square root squared canceled out, and the square root squared, again, canceled out here. You're left with y plus h in the numerator minus y, and h times the conjugate. We don't need to go ahead and distribute these. We can just leave it as it is. Our h's cancel out. And we'll be left with the limit as h approaches 0 of 1 over the square root of y plus h plus the square root of y. We go ahead, we plug in 0 for h, and this is going to reduce to 1 over 2 radical y. That is our k prime of y. Okay, so again, this is the general form of the derivative, or the slope at the tangent line. Okay, now we can find k prime of 4. This is a perfect square. This is going to reduce nicely to 1 over 4. Same deal with 1 over 9, 9. This is going to reduce to 1 over 2 times the radical of 9. 1 over 2 times 3 is 1 over 6. Okay, and for that last one, we have k prime of 36. We plug in 36 into the bottom. 1 over 2 radical 36 becomes 1 over 2 times 6 becomes 1 over 12. Okay. So this general form is really useful if we want to plot it, if we want to go ahead and then find the derivative at any specific points. We can always just start with the general form of the derivative. All right. Now, let's talk about graphing. So we can treat f prime of x now as its own function, because it is, and we can sketch a graph of it. Let's see an example of what that looks like. It says sketch an approximate graph of the derivative of the following function. Okay, so we're just given this function over here, and we're going to have to try to estimate, right, or try to approximate what the graph of the derivative is going to look like. Now, to remember, the derivative, right, is the slope of the tangent line at any point. So that's what we need to consider here. Okay, so how is the slope of the tangent line changing as we go across this function? Okay, so I've got some labels here to help. So in these places where, you've got like a maximum on this curve or a minimum on this curve, you're going to have a horizontal tangent line. Okay, and horizontal tangent lines will have a slope of 0. And these are important because this is oftentimes where the slope is going to change from positive to negative. So you can see over here, we're starting off with positive slopes. We're going to 0, and then we're dropping to a negative slope. We go back to 0, and then we go back to a positive slope. Now, it might help to sort of assign kind of made up numbers just in your head to help you think about how this is changing. So if it's going from something really steep, maybe like a positive 5 slope to a positive 2 slope to a 0 to a negative 2 slope, back to a 0 to a positive 2 or positive 3 slope, something like that, right? And those values that you're writing, that's actually what you're going to plot for f prime of x, okay, at every one of these locations. So we come down here. So if this was that positive 5, then that's kind of what we should be expecting here. This should be a 5. And here, where we had that positive 2 slope, this should have a y value of 2. And here, where we have a slope of 0, we need to have a y value of 0 on f prime of x. Okay, so where we drew a horizontal tangent line, that's where the graph of f prime of x should be crossing the x-axis. Okay, and then for this brief period of time, it's negative. Okay, so for in between these 2 points, we should have negative y values. It's going away from 0, it's becoming negative, and then it's coming back to 0 again, which is exactly what happened here. Okay, so it gradually got more and more negative, and then became again less negative to get back to 0. And then after that, well, we have an increasingly positive slope. So if we started with +1, then we might have +2, something like that. And that's why these y values are rising over here on f prime of x. Okay, so this is the process of how you might estimate the slope or draw an approximate graph of f prime of x with the graph of f of x. Let's look at another example. So this function g of x is just kind of coming in with initially a very negative slope, right? And it's kind of easing out and almost flattening out and getting closer and closer to 0. So, and that's exactly what we should be thinking. So we should think maybe this started at -20, then -15, and then -10, -5, -2, -1, -0.5, and so on and so forth, right? So it's getting ever closer to 0. And those slope values, again, are what we would want to be plotting here. Okay, so I've just drawn these hypothetical tangent lines. And those y values that we're making up are what we want to plot. So if this was a -20, then that might be a -20. And then by this point, maybe it's flattened out in a -10. And so on and so forth, right? So these slopes, this value here is essentially just the slopes that you see here. So the slopes are getting from a very negative value to closer and closer and closer to 0. Okay, and that's what this graph reflects. And as a final example, we might have something like this. Okay, so in this kind of case, you seem to have a singular slope. This is just a line, right? So it's not changing. So you might have just a singular slope like -1. On this side, you might have, again, a singular slope like +1. The actual number value doesn't matter in this case, right? But let's think about what's happening at the center here. We have on our graph what's called a corner. And the difficult part of these is that you, in some sense, can actually draw infinitely many tangent lines through this sort of point, right? Because it's kind of just poking out like that. We can fit so many different tangent lines that won't intersect with any other points on this graph. And for that reason, the slope here is actually indeterminate or undefined, okay? So we don't actually try to assign a numerical value to that. So what are we going to do? So if we have a -1 and a 1, and then we have some sort of indeterminate slope here, when we go to graph this, we're going to make sure that we put a hole in the graph at that x equals 0 point. Okay, so the slope is going from, say, a constant -1 to a constant +1, but here at that corner, it's undefined. Okay, and that's partly what allows this to kind of, the slope to jump instantaneously from a negative to a positive without any sort of continuity. Okay, so this sort of thing is going to result in a discontinuous graph for f prime of x. Okay, so these were just a few examples, but hopefully this is a good start. If you found this lecture helpful, please give it a like and subscribe so you don't miss the next one. Thank you for watching.